Okay, here's another practice exam I use with my students. This is only on topic 1. So this is on forces in motion, and its content is on the triple content. So it's for physics only. I mean, there are bits of it which will help you in double science as well, but not all of the questions will be in double science. So it's really paper 2. Yeah, so paper 2 means it's physics only. Double science only take paper 1. Okay, so we've done it as a end of term test for our students to see how well they're doing on their way towards electricity, the next topic. Okay, so the first question is a study of moments, yeah, which only comes in the paper 2 exam. So the question is about a folding table. So it's got a hinge, yeah, and you can let the table down, and presumably it's held up by some kind of force. But let's see. So there's a folding table which rotates around this pivot point. Okay, that's where we're going to take the moments around, and the diagram shows some of the forces acting on the table. Well, how many forces? Well, the weight is trying to turn it clockwise around the pivot. So that's the center of the rotation. And then this force, force S, they've called it, is balancing the moments, yeah, by producing an anti-clockwise turning effect. Remember that moments are turning effects of forces. The weight of the table acts through the point G, yeah. What is the name that we give to point G? Yeah, and the weight of the table is halfway along the length of the table. That means it's the center of its mass or the center of its gravity. Okay, so center of mass or center of gravity are acceptable terms, but you can't say center of the weight. Okay? All right, so the table must be a uniform thickness, uniform density table if the center of the mass is halfway along the length, which it appears to be. All right, they then want you to show that you know the formula linking moment, force, and perpendicular distance from the pivot. Okay? So remember, all distances in moments are at right angles to the direction of the force. So let's just have a look at what that means. So the weight is going up and down, and the direction of the force, the distance to the hinge, is half of the length of the table, which is given to us. So we know D must be 42 centimeters. Okay? So you see that the distance is at right angles. The distance is at right angles to the direction of the force. Yeah? Force is downwards, distance is at right angles to the force, and that's why we must always state that it's the perpendicular distance from the turning point, which I've called the pivot, which is the hinge. Okay? All distances are measured to this point. Now they're telling us, we'll do the next bit in yellow. They've told us that the moment of the weight force is 92 newtons per meter. That means if we multiply the weight, which is the force of the due to gravity, by the perpendicular distance, which we just said is 42 centimeters, is given to us, when you multiply them, it gives you the clockwise moments, which is W times 0.42, but we don't need to know that. We just know it's 92 Newton meters. Okay, so the units for moment are newtons times meters. So we say the moments are in Newton meters. Okay, so that's why they've got it written here as 92 Newton meters. So now we got to use the principle of moments, yeah, to calculate the other force, which is force S in the diagram. that a person is applying to keep the table in equilibrium. In other words, the table's not being held up by anything for now, and it's the force the person is providing to balance the weight, which is trying to turn it down, and the person has to put a force upwards. Okay, this force is 84 centimeters from the hinge or the pivot. Okay, so you can tell automatically the force is going to be smaller than the weight, okay, because it's further away. So the principle of moments, for something to be kept at equilibrium, we know that at equilibrium, the sum of the clockwise moments, this sigma, Greek letter, means the sum of clockwise moments, CWM, is equal to the sum of the anti-clockwise moments. It's always important that you've listened to the audio in these videos to get the full understanding. So we know that the clockwise moments they've given us is 92 newtons per Newton meters. How do we know? There. Okay, they've given it to us in the question. Then we know the distance to the Fs force, yes, is 0.84. So the only unknown is Fs. If you rearrange it correctly, you'll get Fs is 92 divided by 0.84, which to two significant figures will give you an answer of 110 newtons. Okay, so that's how you do the balancing moments. Substitution of numbers gets you 1 mark. Rearranging the equation so you can work out the unknown Fs is the 2nd mark. And please try to show you're working clearly like I have. Yeah? Explain that this is the principle of moments. Show you know what you're talking about. Put the numbers into that equation. Rearrange it for the unknown. And then put your answer to the correct number of significant figures, which will be 2, because the data provided is only provided to 2 significant figures. Okay, in this case they're giving you the units, but always remember, answer must be given with units. The 3-step process. That's why they give you 3 marks. Okay, it then says, state Newton's 3rd law. So it's nothing to do with moments, although they're using this question on moments to see if you know that for every action there is, which is a force, there is an equal but opposite reaction. So it's equal in size, opposite in direction. Okay? Clarity is key in knowing your definitions of Newton's laws. So you need to learn the correct wording for each of the Newton's laws. Okay? So the person who's holding the table up, stopping it from collapsing, yeah, is providing the upward force, and they want you to think about that. State the magnitude and direction of the force that the table is applying to the person who is producing the force upwards on the table. Okay, so that's the reaction to force S. If the force S is upwards, then the reaction force must be equal in magnitude, so it must be the same as what we put in the last answer, which is 110 newtons, but opposite in direction, so it must be downwards. So this is how you answer questions on moments and forces. Okay, there are 2 conditions for equilibrium. Up and down forces must be balanced or in equilibrium, and clockwise moments must be balancing anti-clockwise moments. So there are 2 conditions for equilibrium. Always. One involves opposite forces being balanced, and one involves opposite moments being balanced. Okay, so here's the mark scheme. I'll let you stop the video if you want to see their way of getting the marks. Okay, POT means power of 10 error. If you forgot to change centimeters to meters, you would have had a power of 10 error. Okay, that's it for question 2. It's the first question in this paper, was the question 2 from the exam that I took it from. And here is another question, which is paper 2 content only, yeah, and it is on momentum. So it shows a neutron approaching a uranium nucleus. This neutron is traveling fast at 2,200 initial speed, 2,200 meters per second, and collides with a slow-moving uranium nucleus traveling at an initial speed for the uranium nucleus of 10 meters per second. Okay? So what happens, this is before the collision, they both have momentum. But they want you to now state the formula linking momentum, mass, and velocity. Momentum is always given by the letter P, mass is always given by the letter M, and V is velocity is the standard letter for it. Best written as words, but if you see the way I put the arrows from the words to the symbols, which are the standard symbols, that should suffice in terms of the exam. That will get me my mark, because the examiner can see that I've referred to the words using the symbols and the arrows. I think that's a good, quicker way of then writing the words out. Calculate the momentum of the neutron. Well, we know the velocity of the neutron was 2,200 meters per second, and they've given us the mass in standard form. Protons and neutrons are approximately 10 to the minus 27 kilograms. Okay, all subatomic particles, that is roughly the mass. So all you got to do is multiply the mass of the neutron by the initial velocity of the neutron. So the initial velocity was 2,200 meters per second. The mass is 1.67 times 10 to the minus 27. Leave it in standard form. Let the calculator do the work. If to 4 significant figures, my calculator will give me 3.674, and I deliberately rewrote it to 4 significant figures. And the power is 10 to the minus 24 now because of the 2,200. And then I got to change that to 2 significant figures because the data provided is only given to 2, or in this case 3 significant figures, and I think 2 is the better one to use. And that's the units you need to know are kilograms, meters, / seconds. So you get 1 for putting the correct numbers together, 1 for doing the correct answer, and 1 for the correct units. Okay? Don't write lots of decimal places. They will probably give you the answer if you had extra significant figures, but there is no need for too many significant figures or decimal places. And then they want you to explain what is meant by conservation of momentum. Okay? The principle of conservation of momentum is that in any interaction, like a collision, the total momentum before the collision must be equal to the total momentum after the collision if there are no other forces acting. In other words, if the only force acting is the forces involved in the collision, then this will be true. That means mathematically, if you know the total momentum before, and then you can work out the total momentum after, you can work out, for example, the unknown final velocity after the neutron embeds itself in the uranium-235 nucleus. Okay, so the diagram 2 shows that when the neutron collides with the uranium-235 nucleus, they combine to create a uranium-236 nucleus, which is an isotope of uranium. In other words, if another neutron goes in, you've changed the isotope from 235 to 236 by adding another neutron in. Now the masses have combined, and you'll have a new velocity. Yeah? So remember, the uranium was going at 2,200 meters per second, and the uranium was initially going at 10 meters per second. We want to find the final combined velocity. Okay? Use this conservation of momentum to calculate V. Okay? They've given us the mass of the uranium nucleus before the collision, and then with the extra neutron added in, it goes up from 3.99 10 to the minus 25 kilograms to 4.01 times 10 to the minus 25 kilograms. So that's the mass of the 235 nucleus, and here is the mass of the 236 nucleus. Now you can see why I handwrite my answers out before, because I'm not so neat with the Apple Pencil as I am with a normal pen. It also means I can go through the answers more quickly. So total momentum before is the momentum we've already calculated for the neutron, yeah, on the other page. And we've got to multiply, we've got to add it to the momentum of the uranium before. Remember, it was moving at 10 meters per second. So the mass of the 235, given above, multiplied by the velocity initially, before the collision, of 10 meters per second. You've got to add this bracketed term to the momentum we calculated over the page in the previous question. And that gives you total initial momentum of 7.66 times 10 to the minus 24 kilogram meters per second. Now, so the total momentum after must be equal to that. Now the mass of the nucleus has slightly increased, yeah, to 4.01. So we can say that this number, circled in yellow, must be equal to mass times velocity after. Yeah? So the mass times the velocity after must be equal to the momentum we just calculated before. Rearrange to get another mark. Put the numbers in correctly, you get 19.1. You can leave it to 3 significant figures, but it's common practice to round up to 2 significant figures as well. So 2 or 3 significant figures will be acceptable in this case. So these 2 questions we just went through, moments and momentum, are only for physics IGCSE students and not double science students. The next 2 questions, however, are common to double science and triple science, so I'm going to do them in a separate video so double science students can also benefit from my solution. Okay, thanks for watching. Don't forget to show your appreciation each time you watch a video. Like, share, make a comment if you want to. It really helps other students see the videos more often. It improves the algorithm from the YouTube rules. The more interactions you have, the more people tend to see those videos. And make sure you subscribe if you find these videos useful. Thanks for watching.